So the two-group design relies on random assignment. The use of random assignment will produce equal groups in the long run as long as you have at least 20 participants. So we need to make sure that we're using random assignment because larger groups give us more confidence that the random assignment has actually produced equivalent groups, right? We want to make sure that we've separated out any differences between people and place them into the different groups so that we don't end up with any kind of systematic differences between groups. So I wanted to give you an example of a two-group design that claims, and I'll just assume that what the researcher is saying is true, that they used random assignment. And let's consider. I don't know what word I want to use, so I'll just say consider. Okay, so in this study, there were women at a South Korean fertility clinic who were trying to become pregnant, and they all had fertility problems. So a researcher from the US got a list of the women who were trying to become pregnant and distributed the names to two different groups of people. For half of the women, their names were distributed to a group of people who were going to pray for their successful conception and pregnancy. For the other half of the women, their names were given to people who don't pray, but instead they were going to keep the woman in mind and hope for them to become pregnant. Like I said, the researcher said that he randomly assigned these women to group. So he had this long list, I think it was 40 something women, who he randomly, he says, assigned to condition, and half of them were prayed for and half of them were thought about. Now, a really important aspect of this design is that the women didn't know that they were being prayed for or thought about at all. This was all just being done for them. They didn't know that they were being included in a study of any sort, anything like that. So it couldn't have been anything that the women were doing or the doctors were treating them differently or anything like that. It was solely the only thing that was going on is that half of the women were being prayed for and half of the women were being thought about. Now we have a larger group. This was more than 40 women, so random assignment should have worked. But what happened by the end of the study is that the women who were prayed for got pregnant at a significantly higher rate than the women who were thought about. And so the researcher published it, and he reported how powerful, I think it's called intercessory prayer is. And other researchers have reported that intercessory prayer like this has been helpful in preventing a second heart attack and a bunch of other sort of medical conditions. So this was sort of a continuation of a theme. But of course, when something like this is published, it makes the other researchers go, I'm curious. Let's see if I can get this same result. So other researchers, at least two different researchers, have attempted to replicate this finding and have been unsuccessful. They've found no difference between groups, whether they were prayed for or they were thought about. They get pregnant at the same rate in the other studies. So, of course, people started questioning the original researcher about his randomization process and things like that, because the simplest explanation is that the groups weren't truly equal in reality. The ones who were more likely to become pregnant were probably in the prayed for group, and the ones who were less likely, and these, who knows why one group would be more or less likely to become pregnant. There are lots of factors that go into fertility treatments and their success. So it's possible that by complete accident through the randomization process, you can end up with groups that are not fundamentally the same. It's possible. Random doesn't always look random. And so it's he might have followed every normal protocol for deciding the randomization. It might have been a table of random numbers. He might have put all the women's names into a hat. I have no idea how he did it, because one of the things that happened is that when people started questioning his methodology, he went dark. He doesn't want to talk to anybody. He gave up his research position at the university where he was teaching, and you cannot find any sign of this guy anymore at all. So it really kind of fuels the speculation that he faked the whole thing in the first place. But I'm going to just assume that he did everything as he said he did in the study, and that just through pure, chance, you ended up with groups that were not fundamentally the same. So when we talk about the power of random assignment, we end up with equal groups in the long run. We think that long run is at least 20 participants, but it might, the larger the group, the more confident we can be that randomization really worked. And so it might be tempting to say, well, I only need 20 participants, but we can't, especially if the two groups end up scoring the same way, we can't really confidently say that you have enough power to know whether the two groups scored the same because the independent variable really doesn't work, or if the two groups scored the same because you didn't really truly randomly assign participants to condition. You need a bigger sample. So I just thought I'd share that study with you as a good example of, even if everything was done right, and I'm just going to assume that he did it all right. I'm trying not to besmirch the guy because people have really not been nice to him. So I'm not going to tell you his name or what school he was at. I will just tell you that, even if he did everything correctly, it's possible that random assignment just didn't work in that situation. And he happened to have placed the women who are more likely to become pregnant into the group that was prayed for. So here's an interesting question. What if there are few potential research participants? So we're not going to be able to reach that 20 or 30 minimum participants. And as a result, random assignment may not create equal groups. What can we do then? Can we still use the two-group design? Well, it turns out, yeah, we can. There are some non-random assignment methods. One of the most powerful non-random assignment method is to do a repeated measures test. In this kind of test, the same participants are going to be tested in both conditions. So one of the powerful aspects of this is that you get rid of all those extraneous variables that you have when you're making between subject comparisons. The groups are by definition equal at the beginning when you do repeated measures because you're testing the same participants in both conditions. So it's really powerful. You get rid of all those extraneous variables. You allow your participants to serve as their own controls, whatever that means, whether it's a placebo type situation or if it's really just this instruction versus that instruction or something like that. Just for your training, it's important for you to know that repeated measures designs are oftentimes referred to as within subjects design. I had called the previous independent group design between subjects, so it's good to know that this design is called within subjects because the comparisons that are being made here are within a single subject or participant. So if a person has produced this score in one condition and that score in the other condition, we're going to make a comparison between those two conditions, but it's within that one participant. So how do we do it? Okay, let's imagine I tried to do my jelly bean test using a repeated measures design. If I was to do that, I would have one group of participants and everybody gets to eat the atypically flavored jelly bean and everybody gets to eat the typical flavor of jelly bean. And they rate the flavor expectation after each of those jelly beans. Okay, so let's imagine I have those really well matched visually jelly beans. So you look at your jelly bean and you think to yourself, well, this is going to taste like cherry. You eat your jelly bean and it tastes like Tabasco. You make your rating. Now I give you a jelly bean that looks almost exactly the same. You look at it and you think, well, it still looks like cherry, but last time I thought it was going to taste like cherry, it tasted like Tabasco. So I guess it's Tabasco. And then you eat it and then you're like, okay, now it tastes like cherry. Not what I expected, right? It would be hard to do this design as a repeated measures design because once you've tasted the cherry flavor first, obviously your Tabasco is going to look surprising, right? So if you got to eat cherry first and you go, yep, I think it's cherry, tastes like cherry, Then you get another one that looks almost identical, and you can't really compare them directly because you already ate the cherry one, right? So all you have is the Tabasco one in front of you, and you go, well, it looks like the same one. And now you eat it. Of course it's going to be surprising because I thought it was going to be cherry. If you eat the Tabasco one first, you go, I think it's going to be cherry. Oh my gosh, it's Tabasco. Really surprising. Then you eat the second one and you go, okay, this one looks exactly like the last one. I guess it's going to be Tabasco. And then when it tastes like cherry, you're going to say, oh, I'm surprised. It's going to be very difficult to imagine how we could administer that flavor taste test in a within groups design where the same people taste both of those Jelly Bellies. It's kind of like asking people to do the Coke versus Pepsi taste test that was very popular in the 1980s. Once you've done the taste test, you can't go back and then taste the other one and think something different, right? Like you've already been through it. The point in belaboring this example is that repeated measures designs do not work for everything. And so while it is a very powerful way of making sure to get rid of any extraneous variables and making sure that the groups start out the same, you can't use it for everything. It doesn't work for everything. So maybe if I have too small of a sample to really count on randomization to work, maybe I'll get around this repeated measures problem by saying, well, what if I do matched pairs? So in this design, we have participants that are measured and equated on some variable. And then we are going to assign from these equated groups. So usually what we're going to be equating them on is some variable that could result in confounding. So we're going to talk a lot about confounding coming up, but basically some variable that could interfere with the impact of the independent variable. So it could be age or sex or experience or anything that the participant brings with them that could cause them to perform differently on the dependent variable would be something that we might want to measure them on and equate them on. So we measure them, we find participants who are equal on that variable, and we put them into pairs. So we try and find, let's say maybe we think sex is going to be an important variable. So we may put people into pairs based on sex. We have pairs of women, pairs of men, pairs of women, pairs of men, if we think sex is going to be that important variable. Once we've got our pairs formed, now we're going to form our two groups by randomly assigning one member of the pair to the control condition and one member of the pair to the experimental condition. So this is where the randomization happens. We have a small n otherwise, but n means number of participants in the sample. So we might have too small of a sample for randomization to work because we might accidentally end up with, let's say, all the women in one group or too many women in one group. This would help to ensure that you've got equal numbers of people with the characteristic in each of the treatment conditions. You end up with groups that are fundamentally the same on that really important variable that you think might interfere. So let me give you an example. Found this nice picture off the internet. Unfortunately, it had 13 people in it and I didn't know how to cut it so it wouldn't look really awkward. So we're just going to say we have 7 women and 6 men available in our sample. We only need 12, so we're going to let somebody go. And you can do that completely randomly. You just sort of say, okay, of the 7 women, one of you gets randomly dismissed. Okay, so now we're down to 6 women, 6 men. Now we're going to assign members to pairs based on their shared score on the variable of interest. In this case, it's going to be sex. So we're going to put 2 women, 2 women, 2 women, 2 men, 2 men, 2 men, right? So we're going to end up with these pairs. Then we're going to randomly assign one member of each pair to each group. So, one member of each pair is going to go into the control group. One member of each pair is going to go into the experimental group. And so we'll end up with equal numbers of men and women in the experimental and in the control group. So we've ensured that our groups are fundamentally the same. But we did it using that randomization, right? So we've got a little bit more confidence that, it's not some kind of systematic bias that allowed us to place the individuals within those groups. All we know is that we've got equal numbers of people with the characteristic of interest in the experimental and the control group. And now we can be more confident that the difference between the experimental group and the control group on the dependent variable is attributable to what we're doing in the study rather than sex, right? So in this particular example, we've controlled for sex by making sure that we have equal numbers in both groups, and we use this matched pairs procedure to do it. Sometimes there are naturally occurring pairs that you can use. So naturally occurring pairs would be things like twins. Oh, we love good twin studies in psychology, right? Because it's beautiful. It's sort of like a naturally occurring experiment. You've got these two people who are biologically related, and in the case of identical twins, they share all their genes, and so it's a natural for wanting to use them as sort of a control for genes and then look for the impact of environment, right? So twins are a good example of, a naturally occurring pair that we might study. Sometimes people use club members or other kinds of social groups as, like graduates of the same university, or people who grew up in the same region, or, cohorts, baby boomers versus, Gen Xers or something like that, as, naturally occurring pairs. And you follow the same procedure as you do with the matched pairs. You have these naturally occurring relationships, and you randomly assign one member to the control condition and one member to the experimental condition. So you still have that random assignment from the pairs into the conditions. So it kind of gives you just this opportunity to kind of, control a little bit about, the characteristics of the people while still randomly assigning. You're sort of controlling for anything that might be an error in your design. So there are things that we can do. Oh, and I noticed that my slide just changed the name of what we're doing here. So at the very top there, you see that bullet point is now called correlated assignment, when previously it had been called non-random assignment. Those are actual synonyms, and apparently I changed my mind about what term I was using as I made my slides. Correlated assignment means that there's some kind of relationship between the members of these pairs, right? So those members are correlated with each other, and we're going to take advantage of that and put one member in each of the groups so that we end up with those characteristics distributed across group. Okay. So it's not always going to be pure randomization when we assign participants, is basically the follow-up or the conclusion of that. All right. Now, so we had our independent variables. Those are the variables that the researcher is going to try and control. The dependent variable will be the variable that's getting measured. So it's the behavior, it's whatever response that the participant is producing, that we're actually going to measure. And we call those DVs for short. So it's the response or behavior that is being measured when we talk about dependent variables. I have a little cartoon I wanted to show you. So the independent variable says, nothing you do affects me. I'm independent. And the dependent variable goes, well, some things you do affect me, right? The idea with a dependent variable, the reason why it's called that is that the individual's score on the dependent variable should depend on whether they experience the experimental or the control condition, right? Their score should depend on the condition that they experienced. Whereas the independent variable should be independent. It is what it is. The researcher assigned or nature assigned, or it is what it is. The dependent variable will vary depending on which condition the person experienced. Our huge hope in life as researchers is that any differences in the dependent variable are directly related to the manipulation of the independent variable, right? Like that's the whole purpose of the study, is to see whether the independent variable causes changes in the dependent variable. So if I tell you to rate the words for pleasantness, will that cause you to have better or worse or the same memory for those words as if you were checking to see whether the words contain ease? Right? Can I cause you to have better memory by giving you one task or the other to perform? So recording or measuring the dependent variable. Well, there are lots of things that you can measure, and I don't know if my list is even completely complete. There are probably fields of psychology that I didn't think of when I was making this list. So my favorite, correctness or accuracy. Rate is another measurable dependent variable, like how many times they performed the behavior within a time frame. So, you might have a rate of 45 button pushes in a minute, or you might have a rate of 15, something like that. How many times you did the behavior within a time frame. The frequency is also a speed measure. So instead of having a time frame, I might just see how quickly you're doing the behavior. And so I might have frequency. Degree, the intensity of the responses. Did they press the lever a little bit or did they press it hard? Did they have a big EEG response in this brain cap or did they have a small one? Amount, the total number of responses. Now you might start to notice a lot of these are going to be linked to each other, right? Because you could imagine that if you have a higher rate, that probably means that you're also doing it faster, right? So the frequency is probably up and your total amount is probably going to be higher, right? So you can imagine that a lot of these dependent variables could be summed up, things like that. Latency, how long it takes from, let's say, the time that you saw the light flash on the screen and you were able to push the button. Like how long did it take before you were able to respond? How long did you spend responding? That would be duration. I mean, these are all just examples of the kinds of things that could be measured. The key thing you'll notice that they all share in common is that they are going to produce some kind of number, right? They're all going to give you some kind of number that then now we could compute statistics. It's become a lot more popular these days to analyze data that's not numerical. But in this class, we're going to just talk about the kinds of things that you would see in our statistics classes, which is, dependent variables that produce numbers, because that's what we can compute statistics on. So like I said, this is not a complete list of all the dependent variables in the world. This is just sort of like categories of the kinds of things we might measure. All right, philosophical question for you. Should you record more than one dependent variable? Well, I'm going to say you can do whatever you want. You can record as many dependent variables as you want. They are separate from each other generally, and each one will require a different statistical analysis. The key thing is you should only collect dependent variable data if it will actually enhance understanding. If there's some kind of theoretical basis for why you would have that dependent variable included in your study. If you are on a fishing expedition and you don't know whether rate of responding would be a better dependent variable or frequency would be a better dependent variable, you should not run a study with both of those dependent variables and see which one's better. Instead, you should do a pilot study and see which one is better. And then and a pilot study is like, 5 or 6 participants. And then when you go live and actually record data on actual people, just use the one that worked the best with the pilot data. A lot of times, people will propose to run a study with, 5 or 6 independent variables and then, 10 dependent variables, and we'll just see what happens. And it's like, you are never going to understand what comes out of that statistical analysis if you have 5 or 6 independent variables and 10 dependent variables. Like, pick a couple. That's my advice. If I'm ever your research mentor, I will tell you, pick a couple. Because really you should only ever collect dependent variables that you have a plan for how you're going to analyze. And so if your plan is, let's see what comes out, that's not a plan. And so figure out what ones you need and only collect those. Now this I'm talking about in controlled research. Please don't confuse this with how you might conduct research if you were using surveys or scales. And you're doing correlational or descriptive research. That's different. I'm talking about in controlled studies. You can have your 2 independent variables because that's what we're talking about. One independent variable with the 2 levels because that's what we're talking about in this chapter. You can have as many dependent variables as you want. I'm just trying to argue for keep it smaller and only those that you know why you're collecting it, how it will aid understanding, and that you have a plan for analyzing. You don't want to do this. Get all the information you can. We'll think of a use for it later. In a controlled study, you don't want to do that. You don't want to waste your participants' time producing a bunch of dependent variables that you end up not needing. You don't want to waste your time. Once you've got the data, you come back and you try and analyze it. You've got to put it into the computer. You've got to figure out which one you're running. It's all very time consuming. And so you don't want to waste your time. You want to make sure that you're only collecting the data that you actually need. So, characteristics of a good dependent variable. We've already talked about this before, and so I'll just say it needs to be a valid measure of the characteristic or the treatment. It needs to be directly related to the independent variable. Now that might sound pretty simple because you're like, wait, I thought I was supposed to be finding out whether the independent variable caused the score on the dependent variable. So obviously it would have to be directly related, but it's not as obvious as it might sound, right? They need to be directly related to each other. And so, how you determine whether they're directly related is, for one, through your literature review. When you've been reading other people's studies, they'll tell you which dependent variables worked for them with these independent variable manipulations. But sometimes other researchers haven't tried a dependent variable that you're thinking about. And so again, I'm going to advocate for the pilot study, right? Get a few people together, maybe other classmates or people who wouldn't be your participants normally, and see whether it looks like the dependent variable is sensitive to the independent variable manipulation. Because basically what we want is a dependent variable that measures the effects of the independent variable manipulation, right? We need dependent variables that will reflect whether the independent variable manipulation worked or not. The last thing on my list is that it needs to be reliable. That if I were to run this study exactly again, using the same participants and everything else, that I would get the same outcome. I put it last on the list because it's possible that people would score differently, not because the dependent variable is not a good measure, but because they've changed. And so I always like to put that last as like sort of a little caveat that it may not be reliable for these individuals across time, but it should be reliable for the same circumstance with people who are in the same, basic status as the originals. It should produce the same basic results. So I just thought I'd give you some examples of independent variables related to dependent variables. So for example, like instructions to learn or not, that should be a good manipulation to be assessed through a memory test. Having music present while you're studying or not, that should be a good manipulation to be assessed through a test score on whatever they were studying. An independent variable where the material is presented in handwriting versus in typewriting. A good dependent variable would be, accuracy of recognizing the words that were, conveyed. I mean, I just thought I'd come up with a couple of simple examples of what I mean by what these phrases that I used, right? We want to make sure that our dependent variable is measuring some aspect of what the independent variable is striving to do. All right, let's stop here and I will finish up my last segment talking about all the ways in which we can go wrong. So I will see you back for confounded experiments.